Dear students, welcome to lecture 11 on heterocyclic aromatic compounds. Most of this material that I am going to discuss in this video lecture is coming from this chapter 26 from the textbook on organic chemistry by Stanley Pine. Okay, so let us begin this study. What are heterocyclic aromatic compounds? Generally, cyclic compounds which contain at least one atom other than the carbon are known as heterocyclic compounds. These are more abundant in nature, and whenever such heterocyclic compounds are aromatic in nature, they are known as heterocyclic aromatic compounds. So simplest examples are pyridine, in which a six-membered benzene ring has a nitrogen in place of carbon. Similarly, five-membered rings, when substituted with one heteroatom, will give us pyrrole, furan, and thiophene. And similarly, when you have two carbons substituted with two nitrogens in a five-membered ring, we get imidazole. Now, here are some of the examples of heterocyclic compounds which are present in nature and have important biological activities, and are quite some of them are quite useful as drugs. For example, lysergic acid has a benzimidazole ring fused with another saturated ring, and it is a very potent central nervous system compound. Similarly, quinine is an antimalarial. It has a isoquinoline aromatic framework. Then histamine, which is responsible for majority of the allergic reactions, contains the imidazole ring. Guanine, which is present in the DNA, has this substituted pyrimidine ring in it. And another simple pyridine derivative is niacin, also known as vitamin B3. And similarly, there are other heterocyclic compounds of importance to us. Now, these are some of the representative drugs which contain heterocyclic rings, and their sales yearly or total sales for 2016 is given here. So, this drug which contains pyrrole ring, heterocyclic ring, is known as atorvastatin. It is also known by the trade name Lipitor, and it has been for many years the top selling drug of Pfizer, and it has earned $14 billion in total. Similarly, aripiprazole, which is a isoquinoline derivative, it also has a pyridine ring, has been one of the top selling drugs. There are some other compounds, heterocyclic compounds, which contain thiophene rings and are important drug compounds, like the tiotropium bromide. It is also one of the top selling drugs. Then the well-known antacid drug is omeprazole, synthesized by AstraZeneca, and this compound has also been a top-selling drug, fetching almost 5.3 billion for the company. More information on these compounds you can find in this link. So it is quite obvious that the heterocyclic compounds and their chemistry is very important to us. They are present in the natural compounds as well as they are present, these structural frameworks are present in important drug-like compounds. So it is vital for us to understand their structure, chemistry, and properties. So let us start this journey with pyridine. Pyridine, when in benzene you substitute one carbon with a nitrogen, we form a compound known as pyridine. So a benzene is, if you replace this carbon atom with nitrogen, it gives you pyridine. Then pyridine is a resonance hybrid of the following structures, in which you see that these two resonance structures make the largest contribution, whereas these resonance structures in which there is a separation of the charge contribute to less extent. And can you answer this question using this information about the resonance in the pyridine? Then pyridine is also basic, but it is less basic than aliphatic amines. Why this could be so? Because we know that basicity is determined by the ability of the lone pairs to react with acids like H+. So lone pairs on aliphatic amines is present in a sp3 hybridized orbital, whereas in pyridine the nitrogen has a sp2 hybridized orbital. Therefore, if you see, the aliphatic amines will have a larger p character, that means their lobe of the orbital will extend outward out of the molecule, whereas in the pyridine, because of the lesser p character, the orbital is more restricted towards the nitrogen center, and therefore this orbital containing the lone pair is less available to the proton. And that is one of the explanations one can give for lower basicity of pyridine compared to aliphatic amine. So using a similar argument, can you answer this question? Now let us turn towards the synthesis of pyridine. Pyridine can be synthesized in many ways, and one of that is the reactions of carbonyl compounds, that is aldehydes or ketones, with ammonia. So in this example you will find that two molecules of acetaldehyde are reacting with formaldehyde and ammonia to give you pyridine. But pyridine can also be synthesized from a reaction of acetylene and hydrogen cyanide, which both these gases, when they are passed through red hot tube, they will react with each other to give pyridine. And similarly, another compound known as pentamethylene diamine hydrochloride, when it is heated, first initially pyridine is formed, which can be dehydrogenated to give you pyridine. Pentamethylene diamine hydrochloride is first heated, you will get ammonium hydrochloride and HCl as the byproduct. This will give you pyridine, which is heated in the presence of palladium and carbon, and it is dehydrogenated to give you pyridine. Now another method of synthesizing pyridine is the well-known Hansch synthesis. In this, 2 moles of beta keto ester, that means if this is the parent functional group, then alpha and beta. So at the beta position there is a keto group, therefore it is known as beta keto ester. This particular example is known as methyl 3-oxobutanone. When 2 moles of this compound, when they are reacted with benzaldehyde in the presence of ammonia, we get the dihydropyridine derivative, which can be oxidized in the presence of nitric acid to give you the dimethyl 4-phenylpyridine 3,5-dicarboxylate. This is the pyridine derivative. These dihydropyridine derivatives are very important biologically because they have been found to have anti-hypertensive properties. So let us take applications of all these synthesis of pyridine derivatives. It is widely used in the synthesis of an antihypertensive drug known as nifedipine. This is synthesized from 2 moles of methyl 3-oxobutanoate and orthonitrophenylbenzaldehyde. When this is treated with ammonia, it gives you the dihydropyridine derivative formed from these compounds, and this compound is popularly known as nifedipine, which is a very popular antihypertensive drug. Similarly, substituted pyridines can be synthesized using a well-known reaction known as Diels-Alder reaction. In this compound 1,3-butadiene is a diene which is rich in pi electrons, and this compound benzonitrile, because of the electron withdrawing property of the phenyl group, this is a electrophile. Because it reacts with diene, it is known as dienophile. So in this Diels-Alder reaction, dienophile and diene react with each other to form a cyclic ring, which is dehydrogenated in the presence of palladium carbon to give you 2-phenylpyridine. Similarly, fused pyridine derivatives can be synthesized from aniline derivatives. So this compound orthoaminobenzophenone, when treated with 2-butanone, gets first dehydrated to form the Schiff's base. When this is treated under basic conditions in ethanol, it is cyclized to form the fused pyridine derivative, which is a quinoline. Now let us move towards the reactions of pyridine. As we know that pyridine is an aromatic compound, and quite expectedly it undergoes electrophilic aromatic substitution. A carbon is substituted with a nitrogen. This replacement has marked effect on the reactivity and orientation of electrophilic aromatic substitution in the pyridine. And this substitution deactivates the benzene ring, and therefore you will find that for simple nitration reaction, which is quite fast with pyridine and toluene like compounds, it is quite slow with pyridine, and you actually need to heat it under strongly nitrating reaction conditions like nitric acid and potassium nitrate and concentrated sulfuric acid. All these have to be heated at 300 degrees Celsius, then only pyridine will get nitrated, specifically at the third position. So this lower reactivity and orientation can be explained, as we have done with the benzene and its derivatives, using the structures of the intermediates that are formed during the substitution. So if you consider the substitution at the second position, you will find that these intermediates are possible, in which the positive charge is distributed within the ring, and we find that a resonance hybrid structure is possible in which the positive charge is coming on the nitrogen. Such an intermediate is very unstable because an electronegative nitrogen doesn't want to lose electrons. Therefore, the substitution at the second position will be very slow. If we consider the third position, we find that the positive charge is similarly delocalized within the ring, but none of the resonance structures has a positive charge on the nitrogen. So none of them is appreciably unstable. So all of them contribute equally to the resonance hybrid, and therefore they stabilize the intermediate, leading to the formation of three substituted products. Similarly, if we consider the substitution at the fourth position, similarly positively charged nitrogen structure is possible, which will destabilize the intermediate, and thus substitution takes place only at the third position of the pyridine ring. Then we move on to the next reaction, that is nucleophilic aromatic substitution of pyridine, and it is found that the nucleophilic aromatic substitution of pyridine is faster than that of benzene. Can you explain this based on what we have learned so far? And the answer is that because nitrogen being electronegative, it has the capacity to accommodate the negative charge that is being brought into by the nucleophile, and therefore the structure of the intermediate is stabilized. An example of this reaction is known as the Chichibabin reaction. In this reaction, pyridine is treated with a strongly nucleophilic reagent like sodium amide and heated, and we find that a substitution preferentially takes place at the second position of the pyridine ring. This also can be rationalized by considering the contributing resonance structures, and when substitution is taking place at the second position, we find that the negative charge structures, the negative charge is localized on the nitrogen, and this is a very stable structure because nitrogen being electronegative can accommodate that negative charge, and other structures contribute to a lesser extent. Similarly, if we consider the substitution at the fourth position, this also has a resonance structure in which the negative charge is being localized on the nitrogen, and this is also significantly stabilized. But if we consider the substitution at the C3 position, such stabilized resonance structure is not possible. Therefore, nucleophilic aromatic substitution on pyridine ring will only take place at the second or the third position. It is more likely to take place on the second position because that is where the nucleophile is getting more stabilization because of the proximity of the electronegative nitrogen. So in the next lecture we will see the chemistry, reactions and synthesis of pyrrole. Thank you.